Welcome to qnawire.
So here we got a, let's see, a Rankine cycle. It is ideal. And we have, let's see, we have a process heater here. We have a reheat portion, um, bleeding off the turbine, going back to get reheated and coming back to the turbine. We could either consider this as two turbines or one. And then we have some of that also coming off into the process heater, and then we have a mixing chamber here. Stuff coming out of the turbine goes to the condenser, then goes to the pump to get pumped up to the same pressure as here, so all this can get mixed. Then it goes to another pump to pump it up to the boiler pressure, which then heats it up and sends it back to the turbine to get work extracted out of it. So let's see here. They say let's see here. The mixture is then pumped to the bottom affected during the heating process. Okay. So did they actually say to part of the steam is extra? I don't think they actually said so, but I'm assuming that the work in these pumps are negligible, which is really a very accurate assumption. And that means that the enthalpy at 1 and at 2 are roughly the same. So the enthalpy at 3, we can get that because we know we have a saturated liquid at 1 megapascal. We're given actually what we need out of the process heater to be 7 megawatts. We want the power out of the turbine to be 3 megawatts. So the pressure in the boiler, we got that. And the temperature out of the boiler, given that, so we can get the enthalpy and the entropy. We know the pressure at 7 is 1 megapascal, and it's isentropic from 6 to 7, so we can get the enthalpy at 7. At 8, we know the pressure and we know the reheat temperature is back up to 500 degrees C, so we can get the enthalpy and the entropy. The condenser pressure is 15 kilopascals, and so we know the entropy at the inlet of the condenser is the same as that at 8 here, coming into the turbine. And so then we get a quality factor of 96.65% and an enthalpy of specific enthalpy of 2,518.8 kilojoules per kilogram. Now, make my dot a little more. That didn't really do any good. Make my dot a little more clear on there. So we can figure out what m dot 3 is. So that's the flow through the process heater, because we know the enthalpy in the inlet and the exit, and we know the power or the rate of heat flux we need out of it, and so we get 2.99 kilograms per second we need of steam coming through the process heater. Now the work performed, the power generated by the turbine, we know that it is m6 times the change in enthalpy from 6 to 7, plus m9, m.9, the work here, or m.8, same thing, times the enthalpy change from 8 to 9. Now we have, let's see here. So we know this, or we know what we want from that. We know this, and we know these, so we can get m6. And so that winds up being 3.873 kilograms per second, which then means we can figure out what m9 is, because that's just this minus this, right? So we bled off about 3, so we're left with about 0.881 kilograms per second going through the condenser. Oh, and I forgot to put in some, let's see here, we're getting some heat out of the process, the process heater too. Now, let's see here. Do an energy balance on this mixing chamber here. And we know everything in here but H4. And we can get H4, and we're going to assume, again, that H4 and H5 are roughly the same, and that basically the work into this pump is negligible compared to, it's easily 10 kilowatts, and here we got 3 megawatts. So, there's orders of magnitude difference here. So we'll make that assumption. And then the rate of heat transfer in, is the mass flow at 5 and 6 times the enthalpy change here, and then the mass flow at, let's see here, at 8, yeah, at 8, or at, yeah, let's see here, is it at 8? Because, let's see here, 7 minus 8, yeah, what's ever coming back in here, yeah, this guy, which is the same as 9, yep. And then so that change in enthalpy during this heating process here. And so that winds up being 12 megawatts. And so we can figure out what this Y is, the ratio of M3 that we're bleeding off here to the total that's coming into the turbine. And that winds up being about 77.3%. So to get this ratio of power, this ratio of heat and power, heat flux and power, we need to bleed off about 77% of the steam on the low pressure side of or the high pressure side of the turbine.